KAUST is unique. It's unique in its resources, it's unique in its location, aspiration, and also the tremendous diversity that we have here. This is a place where people who want to pursue a dream could come in and work on whatever important problems they aspire to solve. The university is going to make the resources available, and all that we are looking for is for people to really have impact in terms of the work that they are doing. We also aspire to be among the best internationally, which is really a tall order for a university that has started only 5 years ago. But we believe that we have the talent, the resources, and we have the ability to really place ourselves where we need to be in the international scene. The faculty here have access to larger projects and centers that are really focusing on big problems and trying to solve problems that are of importance to the kingdom and to the world. It is for me really a mission, how to recreate the glory of science that used to be present in this region 1,000 years ago.
The acquisition of Shaheen 2, a new custom-built XC40 supercomputer from Cray, with perhaps the best integrated memory hierarchy and storage system of any supercomputer, returns KAUST to the top 20 internationally in terms of high-capability computing and the top 2 of any university in the world.
Currently, we know that we use about 20% of electricity globally for lighting. And the objective of my lab is to develop a new technology that hopefully be able to cut back those electrical consumptions. So far, we have developed high brightness, bright color laser. The ultimate goal is to demonstrate the mixing of red, green, and blue laser to generate white color light.
When we think about chaos, typically we think about something that we don't want to put in our devices because it introduces unpredictability. And actually we show that if you use it, you can increase the efficiency of devices by a large factor. One of the implications of our study was let's say, the possibility to engineer a new type of solar cell. The solar cell is based on completely disordered structure, like the brain is based on the neurons, right? Completely disordered unit. This solar cell is based on the same principle and is able to achieve an incredible high performance thanks to the use of disorder. This example more or less characterizes the main principal idea of our research here. So to engineer material which are characterized by different degrees of disorder, randomness, chaos, and unpredictability, and to use this effect to achieve high-level functionalities.
Visual computing is important because it touches so many areas of industry and academia. For example, with virtual reality and augmented reality, lots of new exciting devices such as Google Glass.
Another example I can think of is the rise of all these cell phones. People are taking millions and billions of images, and companies like Facebook or Twitter are really interested in processing all this visual data. So one set of research problems we're interested in is the design of hardware and software for the next generation of cameras and display devices. For example, one of our projects is dealing with capturing fluid in motion, so where we built the hardware and software for that.
Another example would be the visualization and analysis of brain tissue. We're collaborating with the Harvard Center for Brain Science to tackle finding out how the human brain actually works, which is one of the major challenges of the 21st century, and we are working together with them to develop new visualization tools to tackle these challenges.
Simulations are becoming more important in computational science and engineering. In this context, simulations are playing an important role at many different levels. Fundamentally, they are helping us to explain phenomena that we observe in the lab or in nature. They are enabling us to test and validate different theories and computational models of complex phenomena.
As you know, there are many different kinds of cancer therapies, and most of them involve severe side effects to the patient. I'm working on magnetic nanowires for cancer therapy, and those nanowires might provide a better solution, less side effects, and also less costs.
Students who graduate from here are very desirable because of the skills that they have acquired. None of the people who graduated from KAUST spend much time looking for a job. Most people actually had their jobs waiting for them even before they graduated.
The biggest strength of the CEMSE division are first is cross-disciplinarity. My research, for example, had intertwined different areas from material sciences, applied mathematics, electrical engineering, and it's very easy to access these in KAUST, to have this ability to talk to people that comes from different backgrounds and areas.
The skills that I learned from KAUST is to always be up for the challenge and to be confident in public speaking. This is the thing that that really helped me a lot here. And also to always give more than is required in any project that we do, in any research that we do. Don't accept the minimum. Always give more and always do your best.